folks, Eric Shanks, and I'm a technical marketing engineer with Portworx. So to get started, let's go ahead and take a look at what our agenda is going to be today so you can decide where you're going to tune me out or if you're going to tune me out. First, we're going to talk about stateful data on Kubernetes, a little discussion about that, kind of a philosophy thing. And then after that, we're going to talk about Portworx Enterprise and an overview. If you're not familiar with how Portworx Enterprise works or what it is, we're going to talk about that first. Then we'll do a little bit of an installation demo on Portworx Enterprise so you can see how easy it is to get installed and get up and running. And then the last two sections, we're going to talk about two of the new features that are out in 2.12, and that's PX Fast. And then we'll do a demo on our scale out object storage. So let's jump right in. Was a couple of weeks ago, I got asked a question by a colleague who's not actually very familiar with Kubernetes, and they asked me, they're like, aren't the applications that are deployed in a Kubernetes cluster supposed to be stateless? And when I started talking to him about it, I got to thinking, I'm like, well, we used to do things when I was a consultant and I was helping customers starting out with Kubernetes. We'd often start with stateless applications because state in Kubernetes is a little bit more difficult. There's no reason to put extra burden on yourself when you're trying to learn a new concept. So a lot of times we started with stateless applications. But a lot has changed since Kubernetes first came out, right? And I'm here to tell you that Kubernetes is for stateful applications as well as stateless. But let's kind of defend that argument a little bit. First off, upstream Kubernetes, the open source team, are working on new storage features all the time. Some of my examples here are, we have persistent volumes and persistent volume claims. We've got storage classes built right into Kubernetes. We have stateful sets that allow us to use those persistent volumes. We've got container storage interfaces that allow us to connect to any storage appliance that supports it. And they're building a new standard for the Container Object Storage Interface, or COSI, which is in alpha right now. Also, we've got bucket classes and bucket claims that go along with COSI. And maybe the best evidence for, the idea that you can store state in Kubernetes is Kubernetes stores its own state in Kubernetes, right? We have etcd that stores the state for how our Kubernetes clusters is operating, and most flavors of Kubernetes have etcd built into the Kubernetes cluster itself. Now, some statistics in 2020, IDC said that 55% of users are running stateful applications in production, and they were expecting that to increase by about 3 times by 2023, which is right around the corner here. So as far back as 2020, over half of users using Kubernetes in production were using it with stateful applications. Also, another statistic here that in 2022, more than 60% adoption for stateful applications in Kubernetes so far. So, at least we're showing that at least 50% of customers that are running Kubernetes in production are actually doing stateful workloads in production. There's a community involved in data on Kubernetes. I met some of these folks at KubeCon this year. And they're very passionate about just having state running data on Kubernetes, right? And each year they put out a report the last 2 years. They hire a third-party firm called ClearPath Strategies to do this survey. I think it's like 500 different customers that are using data on Kubernetes, and just to ask them questions, right, to figure out how they're using data. Some of the interesting information that came out of the report, which you can go and download yourself if you'd like, just going to run through a couple of those here that I found really interesting. The first one was the factors in decisions to run data on Kubernetes. Why would you want to run data on Kubernetes in the first place? The number one reason was to ensure consistency. Now, it doesn't necessarily say what consistency means, but to me, I'm assuming this really means that I have a consistent deployment and operational strategy for the data that I'm running, regardless of maybe what cloud I've got that data on, right? I don't have to learn one database solution for, say, AWS and another database solution for vSphere and another database solution for Azure. I'm getting some consistencies because of that Kubernetes platform layer. The second one on this list is also simplify management. And I'm guessing that simplify management goes very closely with that ensure consistency. Once I've got a consistent infrastructure, management becomes easier, right? So those two are almost together. And then if we look down a little further, like line 5, standardizing on Kubernetes. Again, standardizing on Kubernetes is very similar to the consistency argument again, right? So it's a repeating theme here that we want to have data that's consistent on our Kubernetes clusters, and it's easy to manage because we have one way to manage them. So some of the benefits to running data on Kubernetes, right? We saw why we wanted to run data on Kubernetes. What are the actual benefits that these customers were getting by running data on Kubernetes? I found it interesting that the #1 reason here was ease of scalability. Now, if you look back at what we were hoping to get out of data on Kubernetes, that's not listed. So it's an unintended consequence of running data on Kubernetes that we get this ease of scalability. So that's a plus. Luckily for us, #2 also shows that the ability to manage all workloads in a standardized way, that is what we were going for with running data on Kubernetes based on those top responses. And #3 here is also consistent environment from dev through production. Again, we're talking about consistency here. So really, we're trying to run Kubernetes data on Kubernetes for consistency, and we're really actually getting that as well. Another point that they found as part of their survey was the productivity that they gained from running data on Kubernetes. Now, the stats here show that pretty much everyone was getting at least 10% or more additional productivity after running data on Kubernetes. In fact, most of them were getting 50% or more, but almost all of them are getting 10% or more. The interesting point about the data here is that productivity goes up when running data on Kubernetes, not just for the leading companies, but also for people who are just getting started, right? People are lagging behind on maybe introducing Kubernetes. As they're starting to use Kubernetes and start putting data on there, they're automatically starting to see that 10% more productivity gain, which is good to see, right? You don't have to be a very mature Kubernetes shop to start seeing some of these productivity gains. And lastly, this one's not necessarily to prove data on Kubernetes, but just out of curiosity, what kind of workloads are actually being run on Kubernetes from a stateful point of view? And this is important to me because sometimes you get those point solutions where you've got a single use case or a corner case that Kubernetes might work for you really, really well. And everything else kind of doesn't. But we're seeing here that people are running databases, they're doing analytics, there's AI and ML, which you hear about a lot in Kubernetes, just persistent storage. There's all kinds of things that are being used on Kubernetes, not just that one use case like AI and ML or something like that, right? So it's pretty flexible on what kind of data you want to store in Kubernetes as well. Now, I will admit that running stateful apps in Kubernetes in containers is hard. First, you have to find that ideal deployment method, right? There's lots of ways that you can deploy databases. For example, like maybe you have to go out and find the perfect YAML manifest and edit it to meet your needs, or maybe you find a Helm chart, or you've gone out to Operator Hub and you found the operator that will work for the database that you're choosing. It's a little bit difficult. It's a little challenging. We've got now a requirement, the combination of flexibility and portability of containers with the benefits of persistent storage in stateful contexts, right? Anytime we put data in Kubernetes, it makes it a little bit harder for us to move those applications around because that data acts kind of like an anchor, right? It's harder to move data. There's more things to move around than just a stateless application. Some storage solutions have limits to the number of initiators or connectors that you can have to an array or service, right? If I'm running my applications in Kubernetes and I'm attaching to an external storage array, for example, there's a certain there's a limited number of connections that I can have for like an iSCSI initiator or something for that node back to that array. So those are things that can kind of get in the way. EBS has the same problem. You can only connect like 40 EBS volumes to the same EC2 instance in AWS. So that's also a bottleneck sometimes. We've also got requirements for simplified day 2 operations, right? As soon as I've got databases in my cluster, I can no longer just delete everything and start up something new. Now I've got data that I have to take care of. So now I have to manage things like upgrades. I have to be able to monitor it. I have to be able to get some observability into those containers to see what's actually happening, so that I can troubleshoot issues if they come up. And backups and disaster recoveries is now a concern, right? As soon as I put data in there, I have to have a way to protect that data, and I have to be able to restore that data in case something happens. So the end goal here is data is living in Kubernetes. People are getting lots of benefits out of running data on Kubernetes, and it's possible that you should start using data on Kubernetes as well, so that you can get some of those productivity gains. I thank you for allowing me to vamp on this concept here for a little bit at the beginning of this session. I thought it was important to dispel any myths about whether or not state should be running on Kubernetes clusters or not. And I think we've kind of proven our case, which is great for me because about 2 months ago, I left my job to come work for Portworx, which focuses on managing data on Kubernetes. So I'm glad that I made the right decisions there. Speaking of Portworx, let's talk about Portworx Enterprise. If you're not familiar with Portworx Enterprise is our software-defined storage that runs inside of your Kubernetes cluster. It acts as a software overlay to your physical disks, right? So you can take internal disks, local attached storage disks that are in your Kubernetes nodes, or you can take disks attached to your nodes from like your SAN and connect those directly to your Kubernetes cluster. You can then stretch your software-defined storage across any of those disks in your Kubernetes cluster, and you can make a shared pool of disk resources that can be used by your Kubernetes applications, right? If we're running Portworx, say in the cloud, we also have additional options for getting those storage devices connected to your Kubernetes nodes. We have a thing called cloud drives, which allows us that when you're spinning up your cluster to say, you know what, I'm running this in Amazon EKS or something, I can go out and provision EBS volumes and attach those to my nodes automatically, right? If I need additional storage, I can go get more EBS volumes and attach those to my nodes, and they all become part of the Portworx shared pool that can be used by your applications, right? So that's generally how I'd like to describe Portworx. If you're like a VMware admin or a vSphere or virtualization admin, you might be familiar with things like VMware vSAN, which allows you to take devices and create a storage pool across your nodes and present those to virtual machines, or Nutanix does something very similar. This is basically those kind of concepts, only for Kubernetes. Now, once we've presented all of those disks to your applications, right, we provide those types of things that you might get from a storage array. We're providing those in software. So, you know, once I start deploying my applications that have persistent data, I need to do additional things to those applications. I need high availability and replication, which Portworx is going to do for us. We have other things like I need to have encryption at rest or role-based access controls to the persistent volumes that I've created. Portworx is going to create custom storage classes for us so that we can identify which pools of disks our application might run best on, and their application profile on how that data is being written, so that we can kind of speed up performance for you. Now we've got unified block file, and as of 2.12, we've got object storage for Kubernetes. So if you need block or file, that can be provided right from our software-defined storage layer, and object storage, which we're going to talk about in a little bit. We can also do snapshots of your data, and we can do those snapshots locally in your Kubernetes cluster, or we can store those in the cloud as well. So if you need an offsite backup, we can take care of that. Automated capacity management. So I already talked about EBS volumes, for example, those cloud volumes that if we need additional actual disks, we can provision those and attach those to our nodes for us. But we can also do things like if you're persistent volume is run out of space, we can extend the persistent volume for you. We can do volume placement strategies to make sure that your applications have data on different nodes, for example, or different topologies, so that if you lose an entire availability zone or something, your data is still protected and available for you in another availability zone. So Portworx is taking those physical disks, creating a pool of resources in Kubernetes and applying and allowing your apps to use those. And then we're providing additional functionality on top of those, that software-defined storage layer to help your applications be ready for production. Here's our rah-rah slide. Big point here that we've got #1 cloud native Kubernetes data storage and #1 in enterprise Kubernetes data storage 3 years in a row now. So the net out of this slide is we're pretty good at this. In fact, we're maybe the best at this, according to GitOps. And just to make sure that you understand that we're not a brand new company, we've been doing this for a little while now. We've got some pretty big customers and some pretty big partners, just to kind of ease your mind there. Now I'll talk a little bit about our architectures for Portworx. This, when I look at this from an architectural point of view, and these architectural diagrams really help me understand how Portworx really works. There's a couple of different ways that Portworx can get deployed. The first one is that hyper-converged deployment method, and we've a little bit alluded to this already. But essentially, each one of your storage, your Portworx Kubernetes cluster nodes can have disks attached to those. We create a shared pool of resources based off of the disks that come from each node, right? So my applications might live on one node, but if something happened, I might need to access data that's on a disk from a different node in my cluster. That can all be done. It's part of a shared pool of resources that's shared across all the nodes in my cluster. If we decide to add more nodes to our Kubernetes cluster later on, and those nodes also have disk associated with them, we can then scale out to another node and incorporate their disks into that shared storage pool as well. So the storage can scale along with your Kubernetes clusters in a hyper-converged mode. We also have another method of doing this, and this is a disaggregated mode. And on the left-hand side, you can see we've still got kind of that hyper-converged storage architecture here, where we've got Kubernetes nodes and they have disk associated with them, and they're part of a shared pool. But on the right side, you can see that we've just got a compute cluster. So these are storageless Kubernetes nodes. They don't have any storage attached to those other than just to run the operating system of that node. So we can still run our applications there. This might be a good place for if you've got stateless applications or you've got applications that scale pretty frequently, but you don't need your storage to scale along with your cluster. You can kind of split your cluster up and define which ones are storage nodes and which ones are storageless nodes. So you can use things like auto scaling groups and things like that. If you're in a disaggregated model, we don't show it here, but you can also scale your storage node as well, right? This is just an example. So hopefully that clears things up a little bit on like how we're getting disks and we're creating a storage pool and how you can architect your Kubernetes clusters to use those disks in the way that you see fit. Once we've created those storage pools, you might be asking, well, how do I access that storage, right? Once we've created that storage pool for you, Portworx will then create storage classes for self-service access, right? So anybody who's got access to that Kubernetes cluster will then see a list of storage classes that will help them pick what storage and what profiles and how that storage is going to be used for their applications. These are just Kubernetes storage classes that you're probably used to using with persistent volumes and things. We're creating additional storage classes once the storage cluster has been created, right? But these work the same way as a Kubernetes storage class. If the storage classes that we've created for you by default out of the box don't work for you, don't worry, you can create your own storage classes, and we've got a list of parameters that you can use to configure those storage classes. So things like their file system. You can pick whether you want XFS or ext4 file systems. You can choose a replication factor, meaning when I write data to disk, do I want that data also written to a second disk perhaps on a different node or a third disk, right? We can set our replication factors however we want, 1, 2, or 3, to protect data in case we lose one of our nodes. We've got shared v4 volumes, which are basically NFS volumes that are POSIX compliant, so that we can do things like have read-write many shares. If you've got an application that multiple Kubernetes pods are all writing to the same disk, we can do that as well. We've got priority IO, so if you want to say like these have lower priority than my production apps or something like that, you can specify those as well. We've got an IO profile, which defines how the data is actually being written to disk. We'll set the IO profile for you automatically and just kind of try to identify what your storage profile is. But if you know that your application is going to be doing sequential writes or reads or something like that, you can specify that here, and it'll help speed up your performance to your disks. We can do grouping, we can do placement strategies, things with affinity and anti-affinity rules. We can secure your volumes with encryption, and we can do snapshots. Now, all of those things are important, but we talked about how data on Kubernetes requires us to have business continuity and disaster recovery plans. We've got a couple of options for you there. The first one being a synchronous local metro area option. And the way this works is you've got 2 different Kubernetes clusters that we have a Portworx storage cluster, and we've stretched that storage cluster across both of those Kubernetes clusters for you, right? So that we're sharing our own key value database across those 2 clusters. And then anytime your applications in, say, your site 1 or your production site write data to disk, we would automatically write that data to the other Kubernetes cluster in your secondary site or your disaster recovery site, however you want to call it, at the same time before we commit the data and let the application know that we've committed that data. And this allows us to get 0 RPOs, because every time we write data to disk, we know it's also been committed to the disk in our secondary site. So we can get 0 RPOs here. The limitation is you've got I think it's 10 milliseconds of latency or less to run a local metro area option. If you're trying to protect data at a larger region, right, like coast to coast or between continents or something like that, and your latency is a little higher, we also have an asynchronous replication option for you. In that case, we've got 2 Kubernetes clusters. They each have their own Portworx implementation installed on those. And then we do replication on an interval of 15 minutes, right? But this allows us to have a much higher latency on our connection between those clusters. So kind of to summarize some of Portworx advantages here, we can cut cloud storage costs in half, partially because we're pooling resources together. We can also increase container density beyond cloud provider limits. Again, this is with storage classes or storage costs. There's limits to the number of external disks that can be attached to your Kubernetes nodes. Since Portworx is that shared layer, we only have to connect those disks to a shared pool, and then we can dole them out to individual pods, and we can go beyond those limits. We've got multi-availability zone and regional availability and data protection with our synchronous and asynchronous solutions and replication factors. We've got integration with cloud auto scaling groups so we can scale our cluster, and we're a full data stack. We do availability, security, backup, and disaster recovery all in one place. And we're getting consistent storage experience across clouds, which, as we learned earlier today, consistent experience is really important. Okay, so it's demo time. We're going to jump over, according to Coach Beard here, Ted Lasso fan. And let's take a look at Portworx Enterprise for a second. If we go to central.portworx.com, this is where we would go to create a manifest to deploy our storage cluster. So I can click on Portworx Enterprise, and we've got a few options for you here. There's a free forever option that I recommend you go give it a try. But today I'm going to go through Portworx Enterprise and click continue. And the first thing I'm going to do here is we're building a manifest that's going to deploy our storage cluster for us in a Kubernetes cluster that we've already deployed. There's an option up here to use the Portworx operator. It's the simplest and easiest way to deploy our storage cluster. but then you have to select what version of Portworx you're going to use. We're talking about the new features in 2.12 here, so I'm going to choose 2.12. And then you can define where you want this operator to live, what namespace in your Kubernetes cluster. And we can leave this as the default. You can specify an external etcd database if you want. We can build one for you as we're spinning up the cluster. I'm just going to leave the built-in used. In the environment, you have an option here, right? We need to know whether you're running this on-prem. And if we choose on-prem, you have to define kind of where your disks are mounted, where you're going to have your journal space created, and whether or not you're going to use px store v2, which is a 2.12 version, right? And then we just kind of define what disks we're going to use as our storage cluster here. If I look at the cloud, this is a little bit simpler because we're using cloud volumes. And I can select AWS, for example, and I can have them created using a spec. So you can see here, I'm using GP2 or GP3 or IO1, and I can specify the size of the disks that I want created in Amazon's VPC and attached to our Kubernetes cluster. Right? But I can also just say, I've already got disks created, I want to consume unused disks, or I can say, hey, use these existing disks that I've already got attached to my nodes as well. It's kind of up to you. Under networking, you can see we can choose our data networks and our management networks. We leave those as default of auto, but if you need to specify those in your Kubernetes environment, you can. And then you can change the port as well for our storage cluster. On the customization screen, we're going to ask you whether you're running this storage cluster on one of these types. I'm going to say EKS, and then you can set environment variables. You can use an internal registry if you wanted, if you're not using our existing registry, and we can set authorization and any of our additional advanced features. When you're done and you agree to the terms, you're going to be presented with two manifests here, and you can either look at those, you can view the spec, you can copy the spec, you can download the spec, you can save these two specs in our central Portworx Central location so that you can go get them later. But effectively, you're going to apply the operator to your Kubernetes cluster with this command. And then once the operator has been deployed, you're going to deploy your storage cluster spec. And at that point, those storage classes will show up in your Kubernetes cluster, and you'll be able to start using those. So that's really what you have to do to deploy Portworx on your Kubernetes cluster. Thanks, Coach Beard. Now let's talk about those two features that are new in Portworx 2.12. Those are PX Fast and Scale Out Object Storage. So let's dive into PX Fast first. One of our customers, I won't name them, but they are a service provider that does like on-demand content, and they had problems with performance and latency, and they had kind of a high failure rate when people were requesting videos. We went in and helped them with PX Fast to basically make those videos faster for their customers. And PX Fast is a way for us to give you just fast disk, right? We are touting here that we can do 1 million plus IOPS, and that's based on our configuration that we did in our lab, which was 8 NVMe drives in a single Kubernetes node, and then you can have as many nodes as you want, right? What PX Fast allows us to do is enable multiple workloads to efficiently run to avoid over provisioning. So instead of having to provision a whole bunch of disks just to get the IO you need, even if you don't need the storage space, we're now using those NVMe disks and providing very fast connections to those so that you can get lower latencies and higher throughputs out of those. We're preserving all the capabilities of Portworx while doing this, including snap, clone, security, and migration, all that stuff. And we're maximizing the performance on those NVMe drives. That's really what we're doing here. So kind of a look at this. When we create our storage clusters, we take disks from wherever they might come from, and we create these individual storage pools. Then our volumes are created so that our containers can use those, and they're mapped to through those storage pools. If we replace one of our SSDs with an NVMe disk, we can then use px store v2, which is part of 2.12. And then some of our applications can use that PXFast access to directly access our NVMe drives. And that gives us our high IOPS, our high throughput, and low latency. And really, main reasons why you should care about PXFast, it's fast. That's really all there is to it. We can do 1 million IOPS. We've got near native disk throughput, which we're going to see in just a second. It's high density, and we can use tiered storage in our Kubernetes clusters. Now, I don't have a demo for PXFast. I'll show you where you can get that demo if you want to actually see our results live, like when they do the testing. But what I did do is provided the actual results from the testing. I thought that was the most interesting. So we ran random read and writes at a 60-40 split with a 4K block size. We also ran sequential writes at a 256K block size and sequential reads at a 256K block size. We had 2 different FIO jobs. One of those jobs was to test IO, and it's 24 FIO pods, 3 jobs per pod, 8 FIO pods per worker node. Our throughput jobs are the same, except we increased the number of jobs per node to 16 so that we could saturate our disks and get a good result, so you could see how it's working. So here's the results from our lab and our testing. This is a 3-node cluster. Remember that there's 8 NVMe devices per node across those 3 nodes. And you can see from random read and writes, we got 3.2 million IOPS, divide that by 3, that's where our million IOPS number comes from. In sequential writes, we got 47 gigs per second. In sequential reads, we're getting 69 gigs per second. So these are pretty great numbers, but I don't like to necessarily look at numbers by themselves. I think we need to compare them to see data, to see like how we're really doing. So this test was also performed on 2 of our competitors that are out there as well. I won't name who they are, they know who they are. So if we look at IOPS and a random reads at a 4K block size, you can see we're beating our closest competitor marginally. If you look at latency, we're also beating our closest competitor marginally as well, right? But we're in the lead. When this really shows up though, is when we start looking at writes. So when we look at writes, you can see we're doubling the amount of writes we can do versus our competitors, right? This random write IOPS number is double what our competitors are doing. And likewise, latency for that is also about half, which kind of makes sense, right? So this is kind of dramatic. If we look at throughput, again, sequential reads, you can see here that we're getting 2.9 gigabytes per second, almost 3 gigs per second. Now we're beating our competitors, but the main point of this slide is to show you that our NVMe disks are spec'd out at 3 gigs per second. So we're actually getting right up to the limit of our NVMe disk while using PXFast, but we're getting those additional features as well that Portworx provides. So that's important. If we look at sequential writes, you also see the same thing here. We're at 2 gigabytes per second here, sequential writes on Portworx, and the spec for our NVMe drives is about 2.1. So again, we're right up there against the spec of the device. We can't really go much faster than that. Put those things together, we're doing random reads and writes with a mix, and you can really see their performance stands out. Portworx reads and writes on the left-hand side here, we're doing at least double what our competitors were able to do. In latency, we're at least half of what our competitors were able to do as well. So this is pretty impressive that we're able to get these types of numbers. One more test, just because we don't run FIO as production workloads, right? Let's try to get as close as we can to a production workload. We did PG bench as well. So this is a Postgres application, a Postgres database that we're trying to run commands against the database itself. And we were getting like double transactions per second here versus our competitors. And again, half the latency. So that's really PXFast. You're getting efficiency and performance. You're able to scale your workloads better with PXFast, and you're able to do that storage tiering, which is One of the important things for some of our customers, right? Not everybody's going to need the super fast disks that are kind of expensive. Some of them are going to use older disks as well. We don't care. You provide your disks to our Kubernetes clusters, and we can do storage tiering through those storage classes, and you can define where your applications are going to live, maybe the best place for your applications. If you want to know more about PX Fast, I recommend checking out this video. This is a video done by a fellow colleague, Tim Darnell, who did all of the testing in our lab for our PX Fast as well as the competitors. And you can see in the link exactly how those tests run. You can see the graphs as they come up. It's very well done. You want to check that out, there's a link here so you can go to our YouTube channel to watch that. Moving on to scale out object storage service. So this is the second feature that we were introduced in 2.12. We mentioned earlier that file storage and block storage are already provided by the Portworx Unified Kubernetes Storage Layer, our storage cluster. Now we're also offering object storage services through Portworx. Now, I will mention that object storage is not managed inside of your storage cluster. We're not providing storage from those disks that you're attaching to your Portworx your Kubernetes cluster. The storage is actually outside of that. So we're using Kubernetes as the orchestration layer to allow you to use S3 storage with your applications. So we're using Portworx to do this. And we're using the Kubernetes orchestration mechanisms that are already involved, already embedded into the platform to do this, but we're allowing you to proxy to external S3 storage. This will be compliant with upcoming COSI standards that are coming in Kubernetes. So once that gets released upstream, we'll start using that as well, and everything will be compliant. So how does it work? We've got a few new Portworx objects that you would deploy in your Kubernetes cluster. These are our own custom resource definitions. The first one is a PX bucket class. A PX bucket class is very similar to a Kubernetes storage class. You're going to define how you want your which is similar to a persistent volume claim in Kubernetes. Now, when you create a PX bucket claim, instead of getting a persistent volume like you do with a PVC, you're getting a bucket, and that bucket will be created on S3 compliant storage. Right now, we offer it for pure FlashBlade or Amazon S3. So when you create that bucket claim, we're going to go out and create you a bucket on one of these locations, depending on where you defined it. Once you've created the bucket, you need a way to access that bucket. So we have another object called a PX bucket access object. You create that, and what happens then is a new Kubernetes secret is created and deployed in your Kubernetes cluster. That secret has connection information to your bucket. So then when you drop your custom application into your Kubernetes cluster, you can mount that secret. And then once you've mounted the secret, you can have your application actually connect to the S3 bucket and continue doing work. So here's a quick comparison. If you wanted to look at the storage classes versus a PX bucket class, you can see those here. I've kind of laid them out side by side. On the left hand is a normal Kubernetes storage class. On the right hand, you can see what a PX bucket class looks like. Very similar. You can see that we've got a parameters section down there, and that's kind of where we're defining where our S3 driver is and our endpoint, right? And we give it a name. That's about it. When we create a bucket claim, again, a bucket claim looks very similar to a persistent volume claim in Kubernetes. Here we have to create a bucket claim with a name and a namespace, and then we're just defining what bucket class our bucket claim came from, similar to how a persistent volume claim references a storage class. And now Ted Lasso is telling us it's time for our second demo. And this one will be on object storage. So here I am in a terminal, and I've got some YAML manifests deployed for me already. And the first one I'm going to look at is our bucket class. Here's our bucket class object. I've given it a name of PB class S3, and it's got a region that shows it's US East 2. In parameters, you can see that we're choosing the S3 driver, and we've identified the endpoint where that S3 driver is connecting to, right? So we'll just apply that object to our cluster. Next, we look at our bucket claim, and we're giving the bucket claim a name, S3 PBC, and we referenced our bucket class in the claim. So we know how that storage is going to be created. And we apply that. Now, once we've applied the bucket claim object, we can do a get on the object itself to get details about our bucket claim. When we do that, one of the objects you can see that we get is the bucket ID. We can copy the bucket ID and go to Amazon and paste it in our S3 console. And you can see that we've got a bucket listed here, but there's no objects in that bucket yet. So we created that bucket through Kubernetes. Next, we're looking at our bucket access. This is how we create the secret so that we can connect to those S3 buckets. We got a bucket class name and a bucket claim name in our access, and we're going to apply that. Once we apply bucket access, we can look for secrets. You can see I've got a PXOS credentials S3 PBA. That's what I named our class. And if we look at that secret, you can see what's in it. Base 64 encoded, of course, but I've got an access key ID, a secret key, our bucket ID, our endpoint, and our region. It's all the connection information that your applications might need to know to get to your S3 bucket and perform actions. So on this last section here, you can see I've got an app, and I've got environment variables listed in my application manifest. It's just a container that's got a list of values that are coming from a secret, and that secret is the one we got from our bucket claim access. So we're going to apply that, and once we've deployed our custom application as an example, we can look at those apps to see what was deployed. And I've got 3 apps deployed. And if I look at the logs for any of these apps, they should show me that I'm uploading something to S3. And it says that they're uploading data. If we go back to our Amazon S3 console, you can see that now I've got objects in my S3 bucket. And if I keep refreshing that, you see the object numbers going up to 18, up to 22, and so on. So one of the main reasons that you can use S3 object access in Kubernetes is to let Kubernetes do that orchestration for you. So if you're a GitOps shop and you've decided, you know what, we need S3 object access, you can deploy Argo CD or whatever your continuous deployment solution is in your shop, and you can define your PX bucket classes, your PX bucket objects, all that stuff in your manifest in your Git repo and deploy it. Your applications can then spin up your S3 buckets, mount secrets to connect to those, and do whatever work they might need, right? So this is a really good solution if you're a GitOps shop and you're looking for that kind of thing. And if you want to know more about object storage, there's also a YouTube video there as well. You can go to the link on your screen here. We're going to walk through a very similar demo to one we just went through, but if you want to see this later on, here you go. And also, one of the things I wanted to mention is if there are additional monthly webinars you want to go check out, you found this interesting, you want to go learn more about Portworx and some of our other products, come and check out our Kubits monthly demo. This URL will take you to our list, our Portworx YouTube channel, where you can find additional monthly demos and learn more about Portworx. And I think with that, I'm going to take a look and see if there are any unopened questions. Somebody was curating those for me today.
I don't think we got any questions.
I have one question. What is the first letter in the name of your competitors? Sorry, I'm not going to answer that one. I apologize. Looking at a possible Databricks use case, would Portworx help for DR and backup? I can't say for certain. So Portworx can help you with DR and backup for Kubernetes workloads, whether that's stateless or stateful workloads. We can help you back up the data that's in your Kubernetes cluster for sure. I don't know about the Databricks part of that, but we definitely help with disaster recovery and backup for applications running in Kubernetes. So thank you, Michael, for those two questions. I think that might be it. So just wanted to sign off and say, thank you everybody for spending some time with me today. I really appreciate you're giving up your time for us today, and I hope I'll see you in the next monthly demo. Bye, everybody.